Hello everyone, welcome back to my YouTube channel. My name is Ray, and in today's video I'm going to be teaching you the three types of discontinuities, those being infinite, removable, and jump. For time's sake, I will not be explaining the nature of infinite or removable discontinuities because I already have a video titled Asymptotic Behaviors where I go through all that information. For now, let's start with how to find infinite discontinuities. So infinite discontinuities are essentially vertical asymptotes, and these are the 4 steps that you need to know. Step number 1 is factor the numerator and the denominator if needed. And I say if needed because sometimes either your numerator or your denominator will be in its simplest form. If we take a look at this problem up here, our numerator can be factored out into simpler terms, but our denominator is already in its simplest form, so there's not much factoring we can do. That means that if we follow step 1, all we're going to do is just go ahead and factor out the numerator. So I'm going to rewrite it, 3x squared minus 21x plus 36, and I'm going to factor it out. If you notice, this is one of those problems where you have a leading coefficient that is not 1. If you don't know how to solve this, please make sure you watch my factoring videos before attempting this problem. So now I'm going to just speed through this since I already have a video teaching you guys how to do it. So 3 times 36 is 108. I need to find a number that multiplies to give me 108, but that adds to give me negative 21. That would be negative 9 times negative 12. Or negative 9 minus 12. I rewrite my expression, 3x squared minus 9x minus 12x plus 36. I group these, and then I factor out. So in the first parentheses, I can factor out 3x, so there's going to be x minus 3 inside. In the second parentheses, I can factor out negative 12, and there's going to be x minus 3 inside. I group my 3x and my negative 12, and I group my x minus 3. I take one of them down. So now my numerator is ready. I've done step number 1, and I have factored. Now I can put my function back together. All right, so 3x minus 12 times x minus 3 over x minus 1. I am done with step number 1. I can move on to step number 2. Step number 2 states, cancel the factors that are the same in the numerator and the denominator. So let's take a look at the factors in our numerator, 3x minus 12 and then x minus 3. The denominator is x minus 1. Clearly, none of these are the same, so we cannot cancel anything. And since we can't cancel anything, we're going to ignore number 3, which states that whatever is canceled is a whole or a removable discontinuity. So we ignore number 3 and go straight to number 4, which states whatever is not canceled in the denominator is a vertical asymptote. So let's take a look. Again, we were not able to cancel anything, and our denominator is x minus 1. We need to set this x minus 1 to 0 because we need to find what x is equal to. We add 1 to both sides, and we get that x is equal to 1. What does this mean? Well, it just means that we have an asymptote, a vertical asymptote at x equals 1. We have an infinite discontinuity over here. All right, now let's take a look at removable discontinuities. So if we take a look at the rules to the left for removable discontinuities, they're pretty much the same rules we use to find the vertical asymptotes. First we factor, then we cancel, then we see whatever's canceled out, and then number 4, we're skipping it out because we do not need to go and figure out where the vertical asymptotes are since we're only focusing on removable discontinuities for now. So the first step is to factor the numerator and the denominator if needed. So the numerator is the same one that I used in the last example. So I just went ahead and wrote the factored form so that I didn't factor the same expression again. So now that I have my numerator factored, let me see if I can factor my denominator. I cannot because it's in its simplest form. So I go ahead and rewrite this. So it's going to be 3x minus 12 times x minus 3 over x minus 3. Perfect. Let me follow step number 2 now. Step number 2 states cancel factors that are the same in the numerator and the denominator. Let's take a look at our factors. One of them is 3x minus 12. The other one is x minus 3. And then in our denominator, we have x minus 3. These two right here are the same, so they can be canceled out. Great. I canceled out my 2 factors. I did step number 2. Let's take a look at step number 3. Whatever is canceled, whatever you cancel out in your numerator and your denominator, is considered a whole or a removable discontinuity. What does this mean? It means that we take that x minus 3 that we canceled, we write it out, and we set it equal to 0 because we want to solve for x. In this case, we would add it by 3 on both sides and get that x is equal to 3. And what does this mean? This means that at x is equal to 3, there is a hole in the graph or a removable discontinuity. And again, if you do not know what a removable discontinuity looks like, make sure that you go and watch my first video to better understand all of this information and know the difference between vertical asymptotes and holes. Finally, let's take a look at jump discontinuities. Jump discontinuities are just what they sound like. You're jumping from one graph to the other. And in order to have 2 functions, you need to have a piecewise function. The most important part to jump discontinuities is your understanding of how functions look when they're graphed. You need to know how these functions look so that when you graph them, you can see where the jump is occurring. So for example, this is how a constant function would look if f of x equals 2. This is a linear, this is quadratic, cubic, etc. You just need to know how they look because you're not going to have this in your exams or in your homework possibly. You need to memorize it. Let's take a look at this example right here. We have the piecewise function. We have function number 1, which is 3x minus 2. And we're told that x needs to be less than or equal to negative 2. Less than negative 2. The second function is x squared plus 2x minus 6. And x needs to be greater than negative 2. Let's apply what I just told you guys about knowing how these functions look. The first function is linear, right? And it has a positive slope. So it's going to look something like this. The second function is a quadratic, and we know that because the x is being squared. And it's positive right here in front. It's a positive 1. So this quadratic is going to be pointing upwards. These are how my 2 functions are going to look. Now it's time to graph, keeping in mind my x is less than or equal to negative 2, and my x is greater than negative 2. So, I'm going to zoom in a little bit. First, we have 3x minus 2. I know that my y asymptote is going to be at negative 2, but I can't necessarily graph it. I'm going to do it right here just for the sake of visualizing it, but I can't graph it because negative 2 is 0, negative 2. And the rules are telling us that x needs to be less than negative 2, so x cannot be 0. It needs to be something down here. But again, for the sake of this visualization, I'm going to graph it. Right, so our vertical asymptote is, rise 3, run 1. So since we're going down, since we're going less than negative 2, we're going to go down 3. So 1, 2, 3, and run 1. Go down 3, 1, 2, 3, and run 1. 1, 2, 3, and run 1. So it's going to look something like this. right? It's going to look something like this. Starting down here, because these 2 points cannot be included, right? This one's 0, this one's -1. So I'm going to go ahead and try my best to delete these. Ignore the cross, okay? I'm going to try my best to delete these. Perfect. I have my first one. And it's going to be a closed circle because it needs to be less than or equal to -2. Let's go ahead and plug the second function. This one's a quadratic function, right? And it needs to be greater than or equal to 2. This quadratic function would have gone, it would have gone through the origin like that. But since it needs to be greater than -2, it's going to look something like this. It's going to look something like this. We're probably going to have an open circle here at -2. And it's going to go through here and then up towards positive infinity. So clearly we can see a jump between this one right here and this one right here. The graph is discontinuous. There's a jump. And that jump is based on this information that we are given here. So ladies and gentlemen, this is how jump discontinuities look like. It's all about understanding how to graph and sort of visualizing how things are going to look when you graph them. You need to know how your functions look when graphed. You need to be able to graph your functions even if it's not exact or perfect. And you need to be able to know when a point will be closed or open. Again, whenever it's less than or equal to or greater than or equal to, we have a closed circle. When it's less than or greater than, we have an open circle, right? The equal is what makes it closed.